Там запись будет. Hello, everybody. I'm happy to introduce our speaker of today, Azamat Saydaliyev. He's a PhD student from Romanovsky Institute of Mathematics in Uzbekistan, and he will speak about some classifications of non-associative algebras. Okay, please.
First, thank you for the introduction, and I also want to thank organizers for giving me this opportunity to present my talk in this seminar. As was said, I will be talking about algebraic and geometric classification of some non-associative algebras. Let's start from definitions. Poisson algebras arose from the study of Poisson geometry in 1970s and have appeared in an extremely wide range of areas in mathematics and physics. So Poisson algebra is just a vector space equipped with two bilinear operations. And with respect to one operation, it is a commutative associative algebra. And with respect to another operation, it's a Lie algebra. And these two operations must be related with this so-called Leibniz law. If we consider a linear map Lx in here, which is just multiplying x from the left side with respect to the bracket, then the last identity can be written as shown in here. And from here, one can notice that the last identity is equivalent to saying that Lx is a derivation on commutative associative algebra. And delta-Poisson algebra, likewise, is the vector space with two bilinear operations, and with respect to dot, it's a commutative associative algebra, and with respect to bracket, it's a Lie algebra, and they must be related with this last identity. Delta-Poisson algebras arose as a generalization of Poisson and anti-Poisson algebras, and on the other hand, they are well related to delta derivations introduced by Filippov in the work shown below. Delta derivation is just a linear map which satisfies this identity shown in the bracket. And here, when delta is equal to 1, one can notice that it becomes just a definition of derivation. And so one Poisson algebra is just the Poisson algebra. Next, transposed Poisson algebra, similarly, a vector space with two operations. Again, and here we have commutative associative algebra, and with respect to the bracket, it's a Lie algebra, and in this case, it differs with the third identity, and this identity is called transposed Leibniz law. And changing the last identity to the following one gives us the definition of transposed delta-Poisson algebra. And as we can see in here, when delta is equal to 1 over 2, we get the definition of transposed Poisson algebra. So transposed Poisson algebra can also be considered as transposed 1 over 2 Poisson algebra. And it is proven that that this triple is both Poisson algebra and transposed Poisson algebra if and only if it satisfies these identities. Next, the notion of F-manifold algebra. It was introduced by Hertling and Manning in this work. And the systematic study of F-manifold algebras from the algebraic point of view started after a paper by Dotsenko. As for the definition of it, it's just, again, a vector space with two bilinear operations, and with respect to dot, it's again a commutative associative algebra. With respect to bracket, it's a Lie algebra, and it must satisfy this identity. And it is known that F-manifold algebras contain both Poisson and transposed Poisson algebras. Several interesting properties of delta-Poisson and transposed delta-Poisson algebras are given in this work, and we are about to discuss some of them. So first theorem states that if delta is different from 1, then there are no non-trivial simple delta-Poisson algebras. Next, let delta be different from 0, and this triple is delta-Poisson algebra. Then it is F-manifold. As we have seen above, all Poisson algebras are F-manifold, and in this case, we can see that for all delta-Poisson algebras, whenever delta is different from 0, they are in in the variety of manifold algebras as well. But for the case when delta is equal to 0, zero Poisson algebra is F-manifold if and only if it satisfies this shown identity. Next, let delta 1 times delta 2 be different from 1 over 3, and this triple be delta 1 Poisson and transpose delta 2 Poisson algebra. Then it is a mixed Poisson algebra, which means that it satisfies the following identities. As for the case when delta 1 times delta 2 is equal to 1 over 3, authors provide this counterexample. So consider the following 5-dimensional Poisson type algebras and set delta 1 1 over 3 beta and delta 2 is equal to beta. Then it is delta 1 Poisson algebra and transpose delta 2 Poisson algebra. And obviously the product is equal to 1 over 3, but it is not a mixed Poisson algebra. Next, let delta be different from 1 over 3 and 1, and this triple be a transpose delta Poisson algebra. Then it is F-manifold if and only if it satisfies this identity. As for the case when delta is equal to 1 over 3, we have this counterexample. So consider the following 5-dimensional Poisson type algebra, and it is 1 over 3 Poisson algebra and F-manifold, but it does not satisfy the identity that was given in this proposition. For the case when delta is equal to 1, we have this proposition. So let this triple be a transposed 1 Poisson algebra. If it is F-manifold, then it satisfies this identity. But the fact that it satisfies this identity does not imply that it is F-manifold algebra. For that, we have, again, this counterexample. So considering this 5-dimensional Poisson type algebra, it is one Poisson algebra with this identity, but it is not F-manifold. So now I want to briefly talk about algebraic classification of algebras with two operations, which we used in our work. So let V with and define T to be the set of all antisymmetric bilinear maps such that this triple is an F-manifold algebra, and here this bold dot theta is a multiplication defined via theta as shown in this formula. And I want to mention that in this case, instead of F-manifold algebras, we can also consider delta-Poisson or transposed delta-Poisson algebras. So the method that we are going to see applies to all of them. So let V be a commutative associative algebra. Then the automorphism group of this algebra acts on T by this action. And we have this lemma stating that two algebras constructed via theta and V from T are isomorphic if and only if there is an automorphism which sends theta to V. So basically this action is decomposing T into orbits which correspond to isomorphism classes. So So consequently, we have a procedure to classify F-manifold algebras with given associated commutative associative algebra. So it consists of three steps. So we should first compute the set T, isomorphisms on T, and from each orbit, which is, as I said, nothing but isomorphism classes, we should choose a representative theta and construct the F-manifold algebra. And as for the results, the algebraic classification of three-dimensional transposed Poisson algebras and Poisson algebras are already obtained in the works shown below. So up to isomorphism, there are 19 types of non-trivial three-dimensional transposed Poisson algebras, and these include one two-parameter family of algebras and 9 one-parameter families, as well as 9 algebras without parameters. As for the Poisson algebras, up to isomorphism, there are 5 types of non-trivial three-dimensional Poisson algebras, and these include just one one-parameter family and 4 algebras without parameters. As for our results, we classified the F-manifold algebras, and up to isomorphism, we found that there are 57 types of them, 57 types of non-trivial three-dimensional F-manifold algebras, and 17 of them are transposed Poisson algebras. One of them is Poisson, and 4 of them both Poisson and transposed Poisson algebras. As for delta Poisson algebras, up to isomorphism, there are 10 types of non-trivial three-dimensional delta Poisson algebras. One of them is Poisson, 5 of them is zero Poisson, and the rest of them are both Poisson and zero Poisson algebras. So next, as for the four-dimensional case, after isomorphism, there are 36 types of non-trivial four-dimensional delta Poisson algebras. And here delta is different from 0 and 1. And in particular, all of them are Poisson and zero Poisson algebras. Next, we have this example, considering the five-dimensional Poisson type algebra. Then for each alpha, it is delta Poisson algebra if and only if delta is equal to alpha. So it means that this algebra does not lie in the intersection of two delta Poisson algebras for different deltas. Thus, from the above theorems and this example, we have this corollary stating that if delta 1 and delta 2 are two complex numbers, and P delta I be the set of n-dimensional delta I Poisson algebras, where I is 1 and 2. If n is greater than 5, then delta 1 is equal to delta 2. Thus, the first non-Poisson delta Poisson algebra with delta different from 0 appears only in dimension 5. So in lower dimensions, all of them are, so we don't have a delta Poisson algebra, which is not Poisson and zero Poisson. Next, we give this theorem for transposed delta Poisson algebras. So up to isomorphism, there are 15 non-trivial three-dimensional transposed delta Poisson algebras with delta not belonging to this set, and 17 non-trivial three-dimensional transposed -1 Poisson algebras, and 31 types of non-trivial three-dimensional transposed zero-Poisson algebras, and among them, three of them are two parameter families, and 9 of them are one parameter families. And there are 26 types of non-trivial three-dimensional transposed zero-Poisson algebras, and among them, 6 are one parameter families. Now, I will briefly talk about the geometric classification of algebras with one operation. So let V be a complex vector space of dimension n, and consider the set of bilinear operations on this vector space, denoted as hom, which is just a shorthand for homomorphism. So fixing a basis from E1 to En, each operation is defined by its structural constants. So for mu, we have this expression, and from here we can see that there are n cubed number of structure constants, because here I, j, and k all change between 1 and n, so that's why we have n cubed number of structure constants. So from here we can see that for each operation we can correspond a point in the affine space Cn cubed. And of course, algebras have defining identities. For example, commutativity, Jacobi identity, and etc. And these defining identities become polynomial equations in the structural constants. The set of n-dimensional algebras of the given variety, which we denote by LT, is just the solution set of these polynomial equations. And this is the set of homomorphisms. So of course we classify algebras up to isomorphism, and an isomorphism is given by change of basis. And this isomorphism defines a natural group action, which can be defined with this formula. And with this action, if the orbit of mu consists of all algebras isomorphic to mu. So thus, LT in this case is decomposed to orbits that correspond to the isomorphism classes of algebras. And with this O mu bar, we denote the Zariski closure of the orbit of mu. Next, we recall some classical facts and definitions from algebraic geometry. A subset of a variety is called irreducible if it cannot be represented as a union of two non-trivial closed subsets. A maximal irreducible closed subset of a variety is called irreducible component, and it is known that any affine variety can be decomposed into a finite union of irreducible components. And by geometric classification, we mean describing these irreducible components of the given variety of algebras. So let's now talk about the definition of degeneration. Let A and B be two n-dimensional algebras satisfying the identities from the set T as we defined above, and let mu and lambda be operations representing A and B respectively. We say that A degenerates to B and write with this arrow if lambda belongs to the orbit closure of mu. And in this case, we have that orbit closure of lambda is inside the orbit closure of mu. So if A is not isomorphic to B, then this degeneration from A to B is called a proper degeneration. If lambda does not belong to the orbit closure of mu, we call it a non-degeneration and denote it with this crossed arrow. Let A be presented by mu, operation mu. Then A is rigid in LT if its orbit is an open subset of LT. And of course, when we consider degenerations, we are only interested in proper degenerations. And the algebra A is rigid in LT if and only if its orbit closure is an irreducible component of LT. Of course, these are the classical definitions and facts, but in our work, we use the methods applied in this shown work. Let me explain this method. Let A and B be two algebras represented by the structures mu and lambda from LT, respectively. And let C, I, J, K be the structure constants of lambda in the basis from A1 to En of the given vector space. So if there exist n square number of maps such that with these maps we can we can construct a new basis for the vector space, and the structure constants of mu in this new basis satisfy this formula. So when t tends to 0, the structure constants of mu converge to the structure constants of lambda. So in this case, A degenerates to B. The basis change that we find for this degeneration, we call a parameterized basis for the degeneration from A to B. Let me provide a trivial example from this method. Take any algebra with basis from E1 to En and products as shown in here. And let's take this parameterized basis. So we are just plugging t in front of every basis vector. Then the product of this algebra takes this form, and as you can see here, we have t outside of this sum. So the structure constants now become like this. So new structure constants just have t in front of all the structure constants. And as t tends to 0, they all vanish, and hence we obtain the multiplication table of trivial algebra. So everything annihilates. And this example shows that any algebra can degenerate to a trivial algebra. And now coming to the results, we did the geometric classification of Leibniz algebras, but let me first define what Leibniz algebra is. So symmetric Leibniz algebra is an algebra which satisfies the following two identities. And any Lie algebra is a symmetric Leibniz algebra. However, the class of symmetric Leibniz algebras is far bigger than the class of Lie algebras. And to obtain the geometric classification of symmetric Leibniz algebras, we relied on the following results. So the algebraic classification of five-dimensional symmetric non-nilpotent Leibniz algebras is given in this work. Next, the geometric classification of five-dimensional Lie algebras is given in this work earlier in 1984. And the geometric classification of five-dimensional nilpotent symmetric Leibniz algebras is given in this last work. And using these results, we obtained that the variety of complex five-dimensional symmetric Leibniz algebras has dimension 24, and it has 23 irreducible components. Now, let's consider the geometric classification of superalgebras and how it differs from the geometric classification that we have with Z2 grading, which means it has two parts, even part, which we denote as 0, and odd part, which we denote as A1. And the elements from these parts must satisfy this relation. Actually, that's what Z2 grading means. And Jordan superalgebra is a superalgebra that satisfies the following two graded identities. The first identity is called supercommutativity, and the second one is called Jordan superidentity. And these bars around elements in power just mean where do these elements belong. So if x belongs to the even part, then it is 0. If it belongs to odd part, then it is equal to 1. So for geometric classification, we take mn dimensional vector space, and the set of homomorphisms is a vector superspace of dimension n cubed plus 3mn squared. And the space has a structure of the affine variety cm cubed plus 3mn squared. To understand this, let's fix a basis. So from E1 to EM, we take the basis of even part of our vector superspace. And from F1 to Fn, we take the basis of odd part. Then any homomorphism is determined by m cubed plus 3mn squared structure constants. To see that, we can analyze these four formulas. Since homomorphism in superalgebra setting must preserve gradation, and the product of even elements must also be even. That's why in this first formula we have only e's, and the indices I, j, and k change between 1 and m. So in this first formula we have m cubed number of structure constants. And in all other three formulas, two elements are two basis vectors are from indices of odd parts change between 1 and n, and the index of even part change between 1 and m. We have m n squared number of structure constants. Since there are three of them, we must have 3mn squared. The rest of definitions about geometric classification for superalgebras are pretty much similar with those that we have seen above, but an important distinction between degenerations of algebras and superalgebras is that in the superalgebra setting, any homomorphism must preserve the Z2 gradation. To illustrate this, we can consider an example. So we are considering two Jordan superalgebras of type 3-1. So this means that even part of the superalgebra has dimension 3 and odd part has dimension 1. So take these two Jordan superalgebras A and B, and looking at them, we can attempt to take the basis change as shown in here. And under this transformation, the multiplication in A becomes like this. And as you can see, it almost coincides with the multiplication table of B, and it just differs with this last part where we have a parameter T in front of E3 prime. But as T to 0, this multiplication converges to the division table suggestion from A. as generation become of beta, as we can see in here, as e as e2 prime, we are taking odd element, but we must take even elements as linear combination of even elements and odd elements with odd elements. In fact, we prove that between the superalgebra A does not degenerate to the superalgebra B. And as for the results, in our work, we have proven that the variety of four-dimensional Jordan superalgebras of type 1, 3 usable components, and type 2, 2 has dimension 6, and it has 25 irreducible components, and the type 3, 1 has dimension 9, and it has 21 irreducible components. And these two works, authors presented the complete degeneration graph, which is also called as Hasse diagram, for the variety of four-dimensional Jordan superalgebras, while leaving several cases as open problems. Investigating those questions, we then prove that there is no degeneration between any of the pairs of superalgebras left as open problems in the above-mentioned works. So this suggests that the degeneration graph they provided in their work is complete. Now we move to the geometric classification of algebras with two operations. And let V be a complex vector space of dimension n, and consider a bilinear operation mu and mu prime on this vector space. So since we are considering the algebras with two operations, we must consider a pair of operations in here. That's why we are taking mu and mu prime. Fixing a basis E1 to En, each operation is defined by structural constants. So as we did in algebras with one operations, in here we can take the structure constants for two operations. And since in algebras with one operations we had n cubed number of structure constants, in this case we have two n cubed number of structure constants. And with them, we can correspond each pair of operations to one point in the affine space C2n cubed. Again, in this case as well, the defining identities of the certain variety of algebras become polynomial equations in the structure constants, and and the set of n-dimensional algebras of the given variety, denoted as Tn, is the solution set of these polynomial equations. And this makes Tn an algebraic variety. Again, we have in algebraic classification, we classify algebras up to isomorphism, and an isomorphism is, as we have seen above, is given by a change of basis, and it defines a natural group action as shown in here. The difference between from the action that we have seen above is that here G is acting both on mu and mu prime. And the orbit of the pair of operations consists of all algebras isomorphic to mu prime. And let T and T prime be two n-dimensional algebras with representatives mu and mu prime and lambda prime. We say that T degenerates to P prime and write with an arrow if this pair of Operations belong to the orbit closure of the pair of operations mu and mu prime. Now, again, considering the practical method that we have seen above, let A and B be two algebras with structure with pair of multiplications, and let's see IGK and DIGK be the structure constants of pair of multiplications of B in the basis from A1 to En. So again, if there exist n square maps such that with these maps we can construct a new basis, and in this basis the structure constants of A converge to the structure constants of B, then A degenerates to B. And again, we call this found new basis a parametrized basis for the shown degeneration. And here I want to note some important fact. Let's take two, for example, F-manifold algebras F1 and F2. As we have seen in the definition of F-manifold algebra, it consists of two parts: commutative associative part and Lie algebra part. So I have denoted them as A1 and L1 in this case, and A2 and L2 for the second algebra. There might exist a parameterized basis change, which gives the degeneration of A1 to A2 and L1 to L2. But to find a degeneration between these F-manifold algebras, these two parameterized basis changes must coincide. So using just one basis change, we must find the degeneration from A1 to A2 and from L1 to L2. And from this, we can see that if either A1 does not degenerate to A2 or L1 does not degenerate to L2, then there is no degeneration between the given F-manifold algebras F1 and F2. Actually, this fact makes it easier to investigate the degenerations of algebras with two multiplication, because degenerations of commutative associative algebras are already obtained, and for the Lie algebras, we also have the results of degenerations. So if we want to find degenerations between F1 and F2, we should only consider the pairs in which the corresponding parts of the first F-manifold algebra degenerate to the corresponding parts of the second one. So as for the results, the variety of three-dimensional F-manifold algebras has dimension 10, and it has 22 irreducible components. And usually simple algebras are irreducible components in almost all well-known varieties. However, in the case of F-manifold algebras, we have found degenerations between simple algebras. As for the delta-Poisson algebras, the variety of three-dimensional one-Poisson algebras has dimension 9, and it has 6 irreducible components. And the variety of three-dimensional zero-Poisson algebras has dimension 9, and it has 5 irreducible components. As for four-dimensional case, four-dimensional Poisson algebras has dimension 16. Actually, the variety of four-dimensional Poisson algebras has dimension 16, and it has 16 irreducible components as well. And for the variety of four-dimensional delta-Poisson algebras, when delta is different from 0 and 1, it has dimension 16 and 11 irreducible components. As for the variety of three-dimensional transposed delta-Poisson algebras, when delta does not belong to this set, so this variety has dimension 9, and it has 7 irreducible components. For transposed -1 Poisson algebras, has dimension 9, and it has 5 irreducible components. For delta equal to 0, the variety has dimension 11, and it has 4 irreducible components. And lastly, when delta is equal to 1, the corresponding variety has dimension 10, and it has 3 irreducible components. So that's all that I wanted to talk about, and thank you for your attention.
No, thank you, Azamat. Some questions, comments, please? No questions? Okay, no questions, no problems. See you next Monday. Bye-bye.
Thank you very much.